All right, hey AP Chemistry. So for section 6.4, a new set of equations come up stemming from the ideal gas law equation. So PV equals nRT, also known as Pivnert or the ideal gas law. This is a very important equation, and this is just like a bunch of plugging and chugging and knowing relationships. P is the pressure in atmosphere, V is the volume in liters, N is the number of moles, R is a constant, 0.0821 liters times atmospheres per mole Kelvin. That's just the units of this constant. And then T is the temperature in Kelvin. So I just wanted to show you how you would use this equation in example. So it says what volume, so I'm looking for V, right? I don't know V. What volume is occupied by 12.5 grams of argon at a pressure of 1.05 atmospheres and a temperature of 305 Kelvin. 305 Kelvin. R is 0.0821 liters times atmospheres per mole Kelvin. And then it asks later, would the volume be different if it were 12.5 grams of helium? Now, argon, if I look up argon anywhere, argon has a molar mass of 39.95. So argon has a molar mass of 39.95 grams. And then, just in case later, helium has a molar mass of about 4 grams per mole. Grams per mole. Now, for the ideal gas law equation, I have to use PV equals nRT. If I have the pressure, and I have the moles, and I have R, and I have T, I could solve for the volume. That can be rearranged, okay? But I left N blank. Now remember, to get moles, and this is way back in Unit 1, moles is grams over the molar mass, or divided by the molar mass. So I'll just do that. My grams were 12.5 grams of argon over the molar mass, which is 39.95 grams per mole. Grams divided by molar mass. If I plug that into a calculator, I get 12.5 divided by 39.95. And I get 0.313 moles. Side note, if I want to do that for helium, I'll have 12.5 divided by 4 is going to be 3.13 moles. Okay. So just as an aside. All right, so I have R, which is a constant. This is a constant that's going to be given to you. You find it. This is for section 6.4. T given to you as Kelvin, 305. Pressure is 1.05. Atmospheres, moles are just calculated. I'm looking for volume. I could do PV equals nRT. I'm going to rearrange it now. If I want to solve for volume, this is an equation that's nice to know. V is equal to nRT over P. And so now I just plug and chug. Moles was 0.313 moles. R is 0.0821 liters times atmospheres per mole Kelvin. Those are just units. T is Kelvin temperature, 305 Kelvin, over P, which is 1.05 atmospheres. Okay, sorry you can't see all that. All right, now if I plug and chug and solve, I will get 0.313 times 0.0821 times 305 divided by 1.05, and I get a volume of 7.46 liters for argon. Now, the question asked, would the volume be different if it were 12.5 grams of helium? You could prove this by calculating it by putting in the value of 3.13 here for moles. The moles are going to be different. If I have the same mass of two substances, I'm going to have different number of particles. We learned that in Unit 1. Clearly, I could see that I have 10 times the amount of moles of helium. And if I go and calculate the volume of helium would be 10 times greater. So you should get a volume of about 74.6 liters if I calculate it with helium. I will do one more question, but I'm going to jump to 41. Before I get there, I want to set you up for 40. For number 40, oops, can't see that. For 40, darn it, you still can't see that. And my flash died. So for 40, it says, what is the pressure in a 15-liter cylinder filled with 32.7 grams of oxygen gas at a temperature of 302 Kelvin? So it wants the pressure. It gave you the volume is 15 liters. And I'm going to have to solve for moles. Oops, can't see that at all. Let me just back this up a little bit. For N, we need to solve moles. The molar mass of oxygen gas, remember, Hofbrinkel. So oxygen is actually O2, is 32 grams per mole. So if I want to get the moles, it'll be 32.7 grams over 32 grams per mole. And you could do that math. The temperature is 302 Kelvin. R is a constant, 0.0821 liters times atmospheres over moles Kelvin, PVTN. And I'm looking for P. If I want to solve for P, PV equals nRT. P is going to be equal to nRT over V. So I'll leave that up to you. You are going to plug and chug and solve that. I want to jump now, though, to number 44. Now, there's another equation that I skipped before, but this is known as the combined gas law equation. It puts all of the gas laws into one combined gas law equation. By the way, for 42, again, PV equals nRT. I'm going to leave it up to you to solve number 42. But for 44, and this is what we'll end with, I'm going to tell you that we're going to use the equation P1 V1 over T1 equals P2 V2 over T2. And that kind of comes from the ideal gas law equation, but it's the combined gas law equation. So it says a weather balloon is inflated to a volume of 28.5 liters. So V1 is 28.5 liters at a pressure of 748 millimeters of mercury and a temperature of 28 degrees Celsius. T1 is 28 degrees Celsius, but remember, we don't like degrees Celsius for these calculations. So I'm going to automatically change this to Kelvin, so 301 Kelvin. So the initial temperature is 301 Kelvin. The balloon rises in the atmosphere to an altitude of approximately 25,000 feet, which is distractor information, where the pressure is now P2, 385 millimeters of mercury. So, sorry, the camera scared me. So the pressure has dropped. Okay. I'm going to move this a little bit. Perfect. The pressure has dropped, so my volume might be increasing. And the temperature also dropped, so my temperature might decrease. So I have increasing and decreasing. My temperature is negative 15 degrees Celsius, but if I add 273, so 273, I get 258 Kelvin. It says, assuming the balloon can fluidly expand, calculate the volume of the balloon, so V2. So I told you this is going to be plug and chug into the combined gas law equation. You may or may not be able to find this equation in your textbook in section 6.3 or 6.4, but I'm giving it to you here. Plugging and chugging, I'll get my volume. Now, this is a bit complicated if I want to predict, but my pressure decreased, so my volume should increase. So I have an increasing factor with pressure, but my temperature decreased, which means my volume should decrease. So I have an increasing and decreasing factor with pressure and temperature respectively. So it's hard to tell if overall it's going to be an increase or decrease. So let's plug and chug into the combined gas law equation. P1 V1 over T1 equals P2 V2 over T2. Plugging and chugging, P1 is 748 millimeters of mercury times V1, which is 28.5 liters, all over T1, which is 301 Kelvin, equals P2, which is 385 millimeters of mercury, times V2, which we don't know, over, let's just say T2, my bad, over T2, which is 258 Kelvin. If you go and solve all of this, right, what I would do is I like to solve all of this on the left side first. So I got 748 times 28.5 divided by 301. And I get 70.8 equals, and then I just like divide these two and times it by V2. 385 divided by 258 equals 1.49 V2. If I were to solve for V, like I just combine these two. 385 over 258 is 1.49. And then I combined all of these and I got 70.8. And now I have 70.8 equals 1.49 V2. Solving for V2, I get 70.8 divided by 1.49. And I get 47.52 liters is my final volume. And so it looks like it overall increased. Okay, so that was just an example of using the combined gas law equation. Use whatever algebra you need to plug and chug my variables in here. This is just plug and chug. Okay, alrighty, so if you have any other further questions or concerns about using the ideal gas law or the combined gas law, just let me know, or you could definitely use this to kind of help guide you through your exercises for 6.4.